it's a little more lively. Okay, so let me put this down for a second. I think I can begin. Put this stuff down. Yeah. So thank you. Oh, sorry. So let me start. Thank you all for joining us once again to the online SPICE and the SPIN+X seminar series, organized between Spin Phenomenon Interdisciplinary Center SPICE that I'm leading together with Karen and Visual City, and the Collaborative Research Center Spin+X between Karlsruhe and Mainz, that is led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. And once again, please know that this is a Zoom webinar style, meaning that you will be hearing the speaker, Stefan Blügel, that will speak next. And please write your questions during the talk, such that I can actually monitor them and then later on pass on the information to each of these questionnaires during the time. And please keep the things formal and nice. Yeah? Just a few words. Stefan Blügel, of course, in our field, does not need an introduction. It's an iconic figure in the world, particularly for schemionics and spin transport from a microscopic point of view. Has a very, very, very long list. You know, he's gray hair like me, yeah, which is nice. Also gray beard like me, which is also nice. Has many awards. You can read them there, but his main contribution to the field is on bringing electronic structure theory to a new level to understand spin physics and spin orbitronics and magnetism in a very united way, also connected to both microscopic and phenomenology within our new synergy grant that is begun with some collaborators to explore the field beyond two-dimensional, go three-dimensionals, and always keep us excited on this front. So with this, let's stop the introduction, and then I would like you please go ahead to share your screen and begin to your talk when you can. Okay, perfect.
Yes, I would like to start my talk thanking the organizers from Kaiserslautern and Mainz for the invitation to the SPICE-SPIN+X seminar. It's a pleasure to be here. And my talk, but the title of my talk is the program of the talk. I would like to explore multi-spin interactions for beyond Heisenberg physics and have a look whether these new interactions can also lead to new chiral particles. I think spin orbitronics kept us very busy in the last 10 years. It's a field where spin-orbit interaction meets spintronics and surprises us with many, many interesting novel properties, many interesting transport properties, but also new particles and or particle textures. On the one you see here on the screen is basically a bunch of isolated, smooth localization, magnetization textures, also known as isolated skyrmions. You see here a ferromagnetic background, and you see here something like looking like an ice hockey puck, and these are the little skyrmions. And the way we can we see these little skyrmions, we see them basically as a magnetization continuum, as a continuous magnetic field. And you see here this continuous magnetization field. You see here the X and Y components in a color wheel. So the X is roughly green and the Y is roughly blue. And black is the Z component, +1, and white is the Z components -1. And these continuous fields are basically entering the micromagnetic energy functional, where we have exchange, Jarodzinski-Moriya interaction, the magnetic anisotropy, and the external magnetic field, for example. And the skyrmion is typically an energy minimizer of this energy function in a certain topological sector. And since we work with topological sectors, it is very convenient that this this magnetization texture is smooth and can therefore be mapped on using topological arguments mapped on a sphere. And you have typically the smoothness allows us that the magnetization density to be characterized by homotopy classes, and the homotopy class is here, for example, characterized by the topological charge, which is for skyrmion ±1. This is a two-dimensional picture. Of course, we embed these skyrmions in a three-dimensional world, and then this skyrmion becomes a skyrmion tube, which has not much structure in the z direction, but new particles can emerge, for example, chiral in 3 dimensions, for example, the chiral bopper, or the globule, or hopfions, where you have which are knotted structures, and with different where the topological charge is replaced by a certain linkage number. What is very important to realize is that some of these objects, like the chiral bopper or the globule, are not only described by a smooth magnetization density, but they are also described, included 2 Bloch points, one Bloch point here and one Bloch point here. On these Bloch points are point regions where the magnetization changes very, very rapidly. So we have not only smooth magnetization textures, but we have also rapidly changing magnetization textures. And these hybrid particles have, of course, very interesting transport properties. One parts where the electron follows the magnetization, parts where you have scattering. And this has been investigated recently in the group of Yuri Mokosov. So what we see is we have this micromagnetic model, which is very convenient for describing the smooth magnetization textures. But this has also limits. We have seen one is the Bloch point. The other one, for example, if you are transition through by a radial collapse from the topological non-trivial state to the topological trivial state, which is the ferromagnetic state, in between, the skyrmion becomes relatively small, and the magnetization texture is changing very rapidly. This is something you cannot catch easily by this micromagnetic model. And therefore, we add a second scale to this modeling, which is the atomistic spin model. And in this atomistic spin model, I have to do one change here. So, in this atomistic spin model, you see that at each atomic site, you have magnetic moments pointing in certain directions. These are the red magnetic moments. And the energy function is consisting of the Heisenberg exchange interaction, the Jalutinski-Morier interaction, the magnetic anisotropy, and here a dipolar field instead of the external field. And and if you take now the continuum approximation and apply this continuum approximation to this atomistic spin lattice model, then you will see that you end up with this micromagnetic model. And that means you have a relation between the spin stiffness in the micromagnetic model and the exchange parameters, the Heisenberg exchange parameters, for example, due to a huge contraction of information. And the same is true for the spiralization in the micromagnetic model and the Jalutinski-Morier interaction in this atomistic model. A second point where this atomistic model becomes very important is when you have competing exchange interactions. For example, here you have, for example, a system where neighboring atoms are coupled antiferromagnetically, but also next nearest atoms like to couple antiferromagnetically. These competing exchange interaction leads in general to very complex magnetic structures. Here I've shown one where you have spin spiral states, canted spin spiral states, or even more complex states. And I would like to point out another important aspect, which is for many of us in the field of spintronics, we're working with metals. And in metals, typically you have a Fermi surface. On this Fermi surface controls the exchange coupling due to properties which are directional dependent on the Fermi surface. And you have, for example, nearest neighbor interaction, which are ferromagnetic and strong, next nearest neighbor interaction, which are antiferromagnetic, and so on. Typically, these interactions are very long range, can lead to many, many lattice constants. And the long rangeness and the competing interactions determined by the Fermi surface plays this important role. And I would like to mention an important aspect. The Fermi surface can change upon the magnetic structure. So the direction of the magnetic structure changes the Fermi surface through the spin-orbit interaction. And at the same time, also the non-collinearity of a magnetic structure, whether you have ferromagnetism or antiferromagnetism, changes the Fermi surface. And therefore, this interaction, Jij, will depend actually on the magnetic structure you are considering. So in order to understand these atomistic spin lattice models, with these parameters J, which are basically described by the underlying electronic structure, we add a third model, which is the density functional model. Density functional theory is very good in calculating total energies. And what we actually do is we compare the total energy landscape of the magnetic configuration basically to this atomistic model or to this micromagnetic model. And often what we conceptually do is we have a starting point, for example, the ferromagnetic state, and then we explore the energy landscape around this ferromagnetic state. And this expansion leads then to these atomistic spin lattice parameters. So that is an important aspect, that these parameters Jij have an initial state dependence. And if you calculate these parameters for the ferromagnetic state or the antiferromagnetic states, these parameters are not unique. Typically, they are different. And so over the time, we developed, the community developed a lot of tricks to calculate purpose-dependent parameters. So before we calculate actually these parameters, we first ask ourselves, for what reason do I need these parameters? Is it parameter for searching the magnetic ground state? Are these parameters needed for thermodynamic properties? Or do I want to calculate magnetic excitations? These parameters, for these different purposes, these parameters might be different. This is, of course, not really satisfying, but it tells you that these atomistic spin lattice models is limited in this capability to describe the magnetic properties under which are a result of the fermionic nature of the electrons. So what is very cool is, if you look at this atomistic model, you have here the Heisenberg and the Jalochinsky-Murray interaction. And these two interactions are exactly diagonalized by a spin spiral state. So therefore, if we calculate the spin spiral state in momentum space, we basically can calculate these interaction parameters J of Q and D of Q, and the Fourier transform gives us these J's. So therefore, you see in many people calculates always these spin spirals. We can calculate the spin spirals without spin-orbit interaction and with spin-orbit interaction. And the difference tells us something about the Jalochinsky-Murray interaction. So basically, the curvature of the energy with respect to Q gives us the spin stiffness, and the slope gives us this Jalochinsky-Murray strength. So we can basically get these micromagnetic parameters. And in a different approach, where we say, okay, we are in the ferromagnetic or antiferromagnetic state or whatever state we are, and then we do a small, tiny perturbation of the magnetic moments and ask, what is the energy change of these perturbations? And this energy change we can relate to these coefficients, these parameters of the atomistic spin model. And for this, we have developed different type of codes to do that technically, which are open source and you can use. Now I would like to come to another point. Typically, we work with metals, and often these metals have large local magnetic moments. For example, manganese has a magnetic moment of 4 Bohr magneton, cobalt typically 2, iron between 1 and 3. So basically, we have large magnetic moments. And that means our spin state is between spin 1/2 and spin 2. Now I remind you at the spin algebra, which has a cyclic ring nature. So if I take the Pauli matrix for a spin half system at side 1 and at side 2 and square it, the highest power which I get is the power 1. So that means, in other words, if you have a spin 1/2 system, and the spin 1/2 system is on two sides, then the highest interaction you can have is Heisenberg, not more. But this rule can be generalized to the spin S. So if you have a spin S, for example, S equal 2 or S equal 1, then this power here has also, this power has still a ring structure, but the highest power is 2S. So that means if you have spin 1, for example, then you would have here the power 3 can be expanded up to power 2. That means, in other words, if you have a spin 1 system, you automatically know that you can have biquadratic interaction because this is 2 times 1 is 2, is a biquadratic interaction. So typically in condensed matter physics, you are often interested in spin half antiferromagnets, because there you have the quantum fluctuation is the largest. And that is a very interesting field of interest where you have spin liquids and so on. We here are often in the other limit that we have large magnetic moments, in particular at interfaces where the coordination number is small, or at surfaces, we have large magnetic moments, and then we have terms which have these higher powers here. On these higher power terms are the higher order spin interactions. And a typical one is, for example, this Fourspin 4-order exchange interaction here. And we call that, if these interactions are important, we call this the beyond Heisenberg solids. So this is a side remark. If you would expand this 4th order term into a micromagnetic model, then you will realize that you have a different power here. You have not only power 2, but you may have even power 4 or power 6. And this is the true skew mechanism, not the one which we use, producing also can also produce localized particles. So in summary, I would like to say these atomistic spin lattice models become important, not also when dealing with beyond Heisenberg solids. But there's a little problem is, so which beyond Heisenberg interactions should I investigate? And for this, our procedure is the following. A good starting point is the multiband Hubbard model. So you see here the multiband Hubbard model. You have here sites. These are the at each side 2 orbitals, and then electrons can hop, for example, from side to side, from one orbital into the same orbital, or from one orbital into the next orbital. So they have different Coulomb interactions, whether the electrons sitting on the same orbital or on different orbitals. You have to think about the Hund's rule, Hund's exchange. Constructing such a Hubbard model, a multiband Hubbard model, which can describe a spin 1 or spin 3/2 system and so on. We look from this Hubbard model into the low energy sector and figure out what are the magnetic interactions out of such a Hubbard model in the low energy sector, which is the spin sector. And you see then, for example, the hopping of an electrons at spins at 2 sides. This gives you the Heisenberg term. Or you see a double hopping here of the electrons at 2 spins here and 2 different spins here at 2 sides. So this is a 4-spin 2-side interaction, it's the biquadratic term. Or you see, for example, a 4-spin interaction here, or a 3-spin interaction. The way we do that technically is basically we write down the Hubbard model. Then this is, of course, a huge model. Then we look into the sector in which we are interested, for example, spin 1/2, spin 1, spin 3/2. Then we look at the quantum number m equals 0 because this is the largest subspace. And then basically we do a Lövdin partitioning up to the 4th order perturbation, and basically project more and more of the Hilbert space into the relevant subspace. And this 4th order means we expand here this exponential into 2nd order and 4th order. So basically what we do is we write down this Hubbard model in these terms of atomistic parameters, hopping parameters, Coulomb views, exchange interactions, and basically having these different terms here. and then basically derive out of this an effective spin Hamiltonian by downfold, by taking the right proper subspace, downfolding it in the subspace of magnetic interactions, and due to the downfolding, we get the correct interaction strength, and from this the correct spin structure, and this basically we do. And if you do that, you get basically this effective spin Hamiltonian, where this is here the Heisenberg term, and these are the additional terms, which is the biquadratic one, the four-spin three-side interaction. So if you have I, J, I, K, and the four-spin four-side interaction, you have I, J, K, L interactions. And I was cheating a little bit because this term you cannot have the Jarodzinski-Moria interaction because the spin-orbit interaction is not included. So with this, this gives us all the interactions up to fourth order perturbation theory. Of course, if you would go now to the sixth order perturbation theory, and you would have, for example, a spin 3 half system, then you would also have here a power 3. And if you go to fourth to eighth order, you would, and you have a spin 2 system, you could also have here power 4, and so on. But we stop at fourth order perturbation. And here I give you a feeling how that looks like. So the effective interaction of the three spin interaction looks like this: as I, as J, as I, as K. So you have basically three sides. One side is visited twice. These are basically the spin operators. You have to transform them into your conventional S matrices or sigma matrices. And then you have also the prefactors here, which are given here. And the prefactor looks like this. It's given then in terms of the hopping parameters, of the different Coulomb view, of the Heisenberg, of the Hund's rule, Hund's exchange, and so on. So in principle, what you could do now is you do an ab initio calculation. You do a Wanyerization of the Hamiltonian. From the Wanyerization of the Hamiltonian, you get basically your hopping matrix elements, and you put this in, and you get your coupling strength Y. We don't do it this way, because I told you what we are actually mapping is total energies. But we could do it this way. But I personally have very little experience in doing that way. But I start looking at it, and I realized that the parameters U, so to say, the screened U and the screened exchange have a certain inaccuracy in the way we calculate them, or has a certain variance in the way we calculate them. And this variance might be good enough for the exchange, for this three-side exchange, but maybe not good enough for the Jarodzinski-Moria interaction in magnetic anisotropy. This requires further investigation. So basically, what I told you, I have not included into my Hubbard model the spin-orbit interaction. And the reason for that is that I'm not clever enough. Because what happens is, if I put the spin-orbit interaction into my Hubbard model, the subspace is not small enough. So because of the spin-orbit interaction, I cross a different subspace which I would like to project out. But if some clever guy in this audience has an idea how to extend that model to spin-orbit interaction, it would be fantastic. Because what you would see in second-order perturbation, you would get this Jarodzinski-Moria interaction. And then due to the spin-orbit interaction, you get also cross terms. And these cross terms would, for example, look like Jarodzinski-Moria times Heisenberg. So you would have additional terms which have a nature which has not been considered so far. And such terms have been investigated recently by the Hungarian group and also by Samir Slubiny's group, where they came up with a number of these type of interactions. But not through the Hubbard model, but through a different approach, which I would like to show you now. So basically, I told you we have this density function theory is good at energies. So we have the ground state configuration, And now we make small variations in the magnetic moment around this ground state. If we do small variations and the magnetic moment doesn't change much, then we can expand the density functional theory energy, because the energy is variational with respect to magnetic moments and the density, up to second order. And the first order term is basically nothing else as the energy change around the Fermi surface, something like this. So the single particle energy is the energy of the electrons in the system. And this single particle energy I can conveniently express by Lloyd's formula, which is given by the logarithm of a Green's function, describing the hopping of the electron and the scattering of the electron on the particular side of the atom. And you have to sum up over all states and take the logarithm in the trace. It looks a little bit complicated, but it isn't. And now you can imagine you have a relativistic system and your electrons, say, for example, you think about Rashba physics or something like this. So basically the hopping electrons contains the spin-orbit interaction. Then the Green's function contains the spin-orbit interaction. I can write down the Green's function into a term which is not dependent on the spin-orbit interaction, and a term which depends on the spin-orbit interaction. This is this B term. And now I basically remember that I do infinitesimal rotations. If I do infinitesimal rotations, this is this S matrix which becomes infinite, the angle becomes infinitesimally small, then this is infinitesimally small, and then I basically can do an expansion of this logarithm like this. And if I exclude all the odd terms because of time inversion symmetry, then I have quadratic terms remaining and fourth order terms, sixth order terms remaining. Now this quadratic term tells you exactly I have an electron propagating from side I to side J, is scattering here and propagates back to the side I, original side I, produces an interaction, and this interaction is, so to say, the lowest order interaction. And since the Green's function contains the spin-orbit interaction, I have basically two terms. One is the isotropic exchange, one is the Jalochinsky-Moria interaction, and and the third term, which I do not consider here very much, is basically a two-side anisotropy. And I can implement, and I can write this Jij now in terms of these A and B coefficients. And you see immediately I have now terms which are proportional to A. This is the, so to say, the Heisenberg exchange. Then I have terms that are quadratic in the spin-orbit interaction. And I have the Jalochinsky-Moria interaction, which is linear in the spin-orbit interaction and proportional to the exchange. And of course, this all are proportional to the scattering matrix. Now, you can immediately imagine what happens if you have now the fourth order term. In the fourth order term, you will get a term which is fourth order in these A's. So this might be my biquadratic term or a four-spin interaction. Then I have a term which is a fourth order in these B's. So this is a fourth order spin-orbit correction. But you can also see that you have mixed terms like AABB or ABBB, and these kind of terms. On these mixed terms producing additional interactions, one of them, which is this Heisenberg-Jalochinsky product, I have shown to you. But other terms are also possible. This has been worked out in detail by Samir Lunis. So now, this is a little bit theoretical. Now, is this important? And so far, we have seen a few systems where this four-spin interaction or this biquadratic interaction is really important. I mentioned two. These are SDM experiments, two layers manganese on tungsten 110. And the other one is this famous skyrmion system, iron on iridium 111. And this is this skyrmion lattice system, which we discussed in 2011. And the most important observation might be that here the skyrmions are not in a hexagonal lattice, but on a square lattice. And the reason why they are on the square lattice is due to this four-spin interaction. And this I would like to show you now. So basically, this is the SDM experiment of one monolayer iron on iridium. What you see here is not the atom, it's a completely different lattice constant. It is the lattice constant of the square lattice of the skyrmions. You see the magnetic unit cell is 1 nanometer. And here I have an artistic view on the magnetic surface unit cell, which is basically such a unit cell. Here, you can see it's 15 atoms. So what we do is basically we do first a spin spiral calculation to understand what the Heisenberg model says. And here you see, for example, for iron on iridium, the energy with respect to the spin spiral vector from the ferromagnetic state to the K point of the Brillouin zone is relatively flat or picks then up. And it looks completely different from iron silver, which is textbook quadratic behavior and so on. So now on top of this, you see now the Heisenberg interaction is basically isotropic. You see the same behavior along all directions. I show here gamma k. This is this direction. I show here gamma m, which is this direction here. So basically, you see the interaction is pretty isotropic around the ferromagnetic state gamma. So this was exchange, and now I add the Fourspin interaction. You see the Fourspin interaction is strongly directional. The minimum is at 90 degrees, which explains you why the skyrmion lattice has a 90-degree structure, a square lattice structure. And wait a second. And this is the energy. So this was the exchange energy which I showed you. This is with spin orbit interaction is the Jaluchinsky-Moria interaction, which you gain energy. And here you have the Fourspin interaction, which is much larger than the Jaluchinsky-Moria interaction and has a minimum at 90 degrees. And now, of course, you can investigate different scenarios. For example, this spin spiral without Fourspin interaction, then you would get this flat one and the total energy would look different. And you can now look at the skyrmion or the anti-skyrmion and the clockwise skyrmion structure. So this is the clockwise skyrmion structure, which I just showed you before. This is the clockwise, which we investigated. This would be the anti-skyrmion structure here. And the energy would be different because the anti-skyrmion, the Jaluchinsky-Moria interaction averages out. And the counterclockwise structure would have the Jaluchinsky-Moria interaction in the opposite direction. So the lowest energy structure is this clockwise skyrmion lattice structure in the square lattice due to the Fourspin interaction. So far, the work was okay, and we knew that the biquadratic term in the Fourspin interaction is very important. Now, I would like to come to a system which is very similar to the system which I showed before, which was iron iridium. Now I show you iron rhodium. Rhodium in the periodic table is just underneath iridium. The electronic structure is very, very similar. The electronic nature is very similar. So what you see here is again the spin spiral calculation. You see here some minimum here, which is would reflect in a non-collinear magnetic structure. You see you have a maximum here at the end point. You see here this is the ferromagnetic state. This the K point is the Néel state. The M point is the antiferromagnetic state. You have the ferromagnetic state again. And everything looks cool until I asked my student to look at what we call multi-Q states. So what these higher order spin interactions do, they are fourth order terms. We have said that the second order term diagonalizes the Hamiltonian. So a fourth order term has basically something like where Q times Q lowers the energy or increases the energy. So you have a mode coupling term. So therefore we look at multi-Q states. There's one multi-Q state here, which is a 3Q state, and there's a 2Q state here and a 2Q state here. And what you see here is that this 2Q state is at a crazy energy. It is totally lower in energy than anything else. So the first question is, of course, you go to your graduate student and say, this is wrong, this cannot be. Because you know, if you include the biquadratic term, this energy here and this energy here has to deviate from this line here the same way, but this is totally different. And so if you plug in, if you calculate now the four-spin terms, you see you have this expression four-spin and biquadratic term changes the energy from here to here and here to here, and the energy should be the same, but it isn't. So some interaction was missing, and the interaction which was missing, we worked out in the Hubbard model just before, is the three-spin interaction. And if you include now the three-spin interaction, then you see the three-spin interaction here subtracts, but here it adds. And the three-spin interaction is huge compared to conventional nearest neighbor exchange, four-spin interaction, or biquadratic interaction. You know, I'm really trusting in my results. I really believe in density functional theory, and I really believe that our theory has predictive power. But I think nobody would believe in the three-spin interaction if you not have an experiment to show it. And I was very, very fortunate to be invited to one of these SPICE meetings and SPICE conferences in Mainz by an organizer or co-organizers, Sinova. And in this conference, I met a student, her name is Jeanette Kemmer. She had a poster. She was the student of Bode, an SDM person at Würzburg. And I talked into her to do this crucial experiment of one monolayer ion on ruthenium, on rhodium-111. And I told her either Bode or the neighboring department of Ralf Claesen or Reinhard, they will have a rhodium-111 crystal for sure. And I worked very hard on her. And finally, she did this experiment. Then she left and the PhD student continued. And you see here this experiment. This is the one monolayer ion on rhodium. This is the SDM experiment. And if you look now at the ripples, of the distance of the ripples, it is not atomic, it's not atom by atom, but it's actually 2 atoms by 2 atoms. So what you see is you have actually these double layers, magnetic double layers, up, down, up, down, as predicted by our theory, which is finally a proof of the existence of the three-spin interaction. I personally was extremely happy that she did this experiment and that I met her on this conference and could convince her to do this. Okay, so now I would like to come to the last point. So far, I discussed these beyond Heisenberg interactions in 2D systems, but I will go now to another class of materials, which are the B20 materials. One famous one is iron germanium. And for iron germanium, we know we have, when we apply a magnetic field, we see a square-muon lattice. The square-muon lattice has roughly a pitch of 70 nanometers. It is a result of a competition of the Jarodzinsky-Moriya interaction and the exchange. But the neighboring element, manganese germanium, which is also B20, it's totally different. Here, you have a 3-dimensional magnetic structure. The magnetic texture is only 3 nanometers, has a period of 3 nanometers, and not of 70 nanometers. And if the pitch has only 3 nanometers, you anticipate already, this cannot be spin-orbit interaction. So there is some unknown interaction, which we cannot explain so far. And I think this falls also in the category of beyond Heisenberg interactions. So now, how to prove this? First, I introduced you the crystal structure. So basically, this crystal structure of 8 atoms, all atoms sitting at weird positions. I think it's called non-Wyckoff positions. And we have germanium atoms and we have manganese atoms. And we have 4 manganese atoms and we have 4 germanium atoms. And what is very important to realize that you have these plaquettes of triangles in this unit cell. They play a role. So we have 4 different magnetic moment directions. And what we do now in the ab initio calculations, we put these magnetic moments in 4 specific directions. So two of them are in the one plane, two of them are in the other plane. The magnetic moments of the atoms in each plane can be changed by an angle theta, and the plane can be rotated to the other with respect to the other plane by an angle phi. So basically, we have a magnetic structure which is described which is controlled by two angles, the angle theta and the angle phi, and basically the angle phi controls the non-coplanarity. So what we do now is, so we have chosen this magnetic structure on purpose because in this magnetic structure, whenever you change phi or whenever you change theta, the Heisenberg interaction remains constant. So any change of the total energy we see must come from beyond Heisenberg interactions. And these are the results. So here for iron germanium and here for manganese germanium. Please look at the scale. The scale of manganese germanium is much larger than the scale for iron germanium. And you see here calculations without spin-orbit interaction and calculations with spin-orbit interaction. So without spin-orbit interaction, the gray, with spin-orbit interactions are dark. And so the energy scale, 60 millieV, this is huge. This is a huge energy scale. So it is really large. And the energy indicates that the higher order interactions are really important. But which higher order interactions are these? That's the question. So at first what we do is, so basically first what we do is we rotate this angle phi to 0. That means now all magnetic moments are planar. And then you can calculate again the total energy as function of this angle theta. And you see a wonderful cosine behavior here. For manganese germanium and iron germanium, the scale is different, but the behavior is very much the same. And it's well described by this fourth order exchange interaction, as you see here. So you need one parameter, and this K boils down to one parameter, and you can fit the entire curve. And then if you go to the non-coplanar situation where you have an angle phi which is 45 degrees, then you see, first of all, this doesn't go down anymore. This doesn't go down to 0 anymore, and the behavior of iron germanium and manganese germanium is different. So now if we add this four-spin term, the four-spin term fits again nicely this iron germanium, but it doesn't fit the manganese germanium. There is something missing here. And so the manganese germanium has a contribution which is coming from the additional non-complanarity. And this we cannot explain by the interactions which I have introduced before. So a novel interaction is needed. And this novel interaction comes about from the kind of topological Hall effect. So basically, when an electron hops on this triangular motif, on this triplet, and you have a non-coplanar magnetic structure, your scalar spin chirality is non-zero. And this scalar spin chirality, especially if the electrons can hop slowly and the wave function can change during the hopping and move adiabatically, then basically you can anticipate, you can think of that this non-complanarity breaks the time inversion symmetry and acts as an effective B field, and this emergent B field basically produces a topological orbital moment where you have a linear relation between this emergent magnetic field and the topological orbital moment. We call that the topological orbital susceptibility. And now think of this spin chirality. Think of this emergent B field, which produces the topological orbital moment. Then you see immediately that you have here somehow a three-spin interaction. This topological orbital moment has basically the susceptibility, and it has here also a vector component which is basically related to the normal of this triangle. And then you have to collect all the topological orbital moments of all the other sides. And then, of course, this topological orbital moment can interact with the spin moment of the atoms. Then you have, so to say, the spin-chiral interaction. And this leads then to the spin-orbit interaction between the spin and the topological orbital moment, which is a kind of a four-spin interaction, which basically is a four-order, three-side interaction. It depends on the spin-orbit interaction. And basically what it does, it is isotropically, it is rotationally anisotropic. It favors a topological orbital moment relative to the triangular lattice. So it can have a positive or negative sign depending on the electronic structure. And in the spirit of the Ampere's current interaction, you can have also now an interaction between the B field, the emergent B field on side 1, and the emergent B field of side 2 of the wave functions, which are interwoven. And by this, you get an interaction which we call the chiral interaction. So basically, you have here then the chiral interaction of side 1, of triangle 1, the chiral interaction of triangle 2. And this gives you basically a six-side interaction. So you have a six-order, six-side interaction. It's covered by the topological orbital moment. It doesn't require a spin-orbit interaction and no external B field. It's all in the wave function. It's rotationally invariant, chiral interaction. And it favors 3D magnetic textures. Why 3D? Maybe you remember from your time of general relativity, where you work with these Riemann-Kartoffel tensors. Whenever you want to describe a curvature, you need 3 legs. And therefore, these 3 legs describe the curvature of the system. So this interaction likes to have three-dimensionally curved magnetic structure. And maybe we can simplify this a little bit and say that the most important one is the on-side triangular plaquette. And this gives you basically this type of interaction. Now, this idea with this curvature, this brought me to the fact maybe we should go back to the continuum lattice. Because in the continuum lattice, you see this curvature aspect much better. So we go back to the continuum representation, expanding the magnetization at side J, at side I with respect to the side J. And then you see the scalar chirality can be represented by a quantity representing, so to say, the tangent, the surface normal, and something which we call a gyrovector field. And this gyrovector field has 3 components and is given by curvatures like this, which look like the Berry curvature. And so basically, the topological orbital moment is nothing else as this gyrovector field times this response function. I remind you that in 2 dimensions we have only one of these components, and this gives you the topological charge. So here in 3 dimensions we have basically 3 components which are contracted out of these 6 terms. And so basically the chiral interaction can now be represented in the continuum limit by the product of these magnetic fields, these gyrovector fields. And it's of course a little bit difficult to see, but this is we call the generalized Fadeev term. And for cubic systems, this tensor becomes a number. And this is the original Fadeev term. And if you add now the Fadeev term to the Heisenberg term, which we haven't discussed so far because that is standard, we get an expression like this one. And this is known from the work of Fadeev, that the solutions produces or can produce Hopfions. And the Hopf number is given by the product of the vector potential, which is conjugate to this vector divergence-free vector potential, and the field, the effective field. And we have not explored this any further so far, but we expect then the solution to become knotted magnetization solitons, like shown here, where the Hopf number is related to the linkage number. And in the same way, we have the spin-Chiral interaction is basically an interaction of this magnetic B field, this effective field, times the magnetization direction. So now the question is this a good concept? How strong is this interaction? Is it true? So now we interpret our results in terms of this new interaction which we postulated, and calculate now this Chiral-Chiral interaction for manganese germanium at this angle of 45 degrees, which looks like that. And if we add this now to the fourth order exchange, then we get a very good representation of this magnetic interaction. And in the same way, we can study now the spin-Chiral interaction, the spin-orbit contribution. Here you see the difference between without spin-orbit interaction, with spin-orbit interaction for iron germanium and manganese germanium. Let's take the difference between the results you see here. And if we take the DMI, you see the DMI to a large extent explains this iron germanium part, but does not explain the manganese germanium part. Although the DMI is of the same order of magnitude, about 3 millieV, you see here also 3 millieV, but the 7-8 millieV here, which are missing, they are actually coming through this spin-Chiral interaction. So I think my time is up. Let me say something about this to the conclusion. I think I introduced to you two new interactions, the Chiral-Chiral interaction and the spin-Chiral interaction. The Chiral-Chiral interaction is a 6-order, 3-side interaction, rooting in the emergent magnetic field of generating topological orbital moment, and basically are ingrained into the wave function of our system. And the second one is related to spin-Chiral interaction, which is a 4th-order, 3-side interaction, which arises as a result between the coupling between the topological orbital moment and the local spin due to spin-orbit interaction. The Chiral-Chiral interaction is rotationally invariant. The spin-Chiral interaction is rotationally anisotropic. It favors a non-coplanar structure of scalar spin chirality of a specific sign. And it dominates in the Jarzynski-Moria interaction in manganese germanium. So there are a lot of things to do in this direction. Especially one of our motivations is to look whether we can find whether this is a fruitful platform for Hopfions, whether there are other materials like the B20 materials which are important beyond Heisenberg interactions, and so on. And I should not finish without mentioning the people: Sergei Grutschuk, Jan-Philipp Hanke, Markus Hoffmann, Bernd Zimmermann, Gideon Müller, Djiba Bouaziz, Nikolai Kiselev, Samir Lunis, and Yura Mokrusov. Without them, of course, it would not be possible to do this complexity of the work. You need many different skills to do that. And maybe the final summary I'll leave to you. I gave a brief introduction to the spin models. I motivated the higher order interaction to the Hubbard model. I sketched also a more rigorous derivation from the DFT. I gave a few examples for multi-Q states, iron iridium, iron rhodium. I introduced two new chiral interactions, the topological chiral interaction due to topological orbital moment in two variations, the chiral interaction, the spin chiral interaction. I give some phenomenological introduction to that when I investigated the manganese germanium P20 system. With this, I come to an end, and I thank you very much.
So everybody's lifting their hands up and clapping. Thank you for a fantastic. Oh, sorry, we could deal with this. Let's stop that. So thank you, Stefan, for wonderful, wonderful talk. And we have lots of questions. So I'm going to start with the ones that were written ahead of time. Let me give the floor here to Wu for a second. Go ahead, Wu, please unmute yourself and ask your question, please. Although there's been some comments already within them, so maybe just a comment. Okay. So sometimes they're muted and they cannot unmute themselves. So it writes in here, is the strength of the high order coupling typically weaker than the Heisenberg interactions? I think Igor already touched upon that, but maybe you want to comment on that. If in your systems this is the case, or if you know of exceptions like the ones that Igor Mastin may have done before.
Could you repeat the first part of the question?
Is the strength of the higher order couplings typically weaker than Heisenberg interactions?
Yes.
So for the higher order couplings, do you have a case where you have a higher, stronger interactions?
It is typically weaker.
Okay.
It is typically weaker, but we found also systems where it's comparable to Heisenberg.
Yeah,
and
Igor
has a very strong impact.
Yeah, Igor Massin notes in here that in some metals, in metallic cases, is found in some systems that is the case. Yeah. Right. So I think, let's move on. I'm going to maybe leave the floor a little bit to first.
I have the impression that you know, these higher spin interactions have, so to say, 4 spins. Say 4 spins versus 2 spins. But if your spins are now very, very large, say 4-Bohr magneton, then of course 4 to the power 4 is more than 4 to the power 2.
Yep.
So in this sense, my feeling is that the large magnetic moments, for systems with large magnetic moments, if the electronic structure is right, these 4 spin interactions or higher order interactions can overpower the Heisenberg interaction.
Yeah, I think this is
purpose. If you look, of course, for systems where the Heisenberg exchange is small, to see the effect of the higher spin interactions. So when is Heisenberg small? If Heisenberg is small, then you are close to a transition between the ferromagnetic state and the antiferromagnetic state. Then Heisenberg does not know what to do.
Yes, essentially, very much according to Igor's comments in here, that once in the metals, when you have that case, the system softens.
Yes.
Close to the interaction, and then this is what is happening, of course. So Abnon, Harni, go ahead and ask or make your comment and ask a question.
Yes. When you presented the Hamiltonian in the beginning, you presented the Dzerzhinsky-Moriya term and the anisotropy term as independent terms. But some 30 years ago, we showed that, in fact, Moriya's original paper had a mistake on the calculation, and those two terms depend on each other. There exists a gauge transformation which removes both of them at the cost of rotating the 2 spins at the end of a given bond. So the resulting anisotropy exists only when there is frustration between bonds, when you cannot rotate all the spins together. So I wonder if that was included in your analysis, and in fact, what was the origin of the anisotropies which you included?
So basically, first of all, I would deeply appreciate if you could give me a link to your paper. Probably I have not read this paper. Second, you know, we talk about the Dzerzhinsky-Moriya interaction. The way I think in my head is that we have Dzerzhinsky and we have Moriya. So Dzerzhinsky basically showed that you can have this type of interactions due to symmetry argument. Moriya put a microscopic picture to it. But there are many different microscopic pictures which gives it finally the same type of interaction. So basically, for me personally, at the end, what I really do is ab initio calculation. I explain only the ab initio calculation in these models, but I also use the model to dig out or to basically do this ab initio calculation in a very particular way, or get into intuition what kind of ab initio calculations I have to do to undig new physics. But at the end, by the end of the day, all interactions are included. I only extract it in a language which describes it in models.
Okay, Jürgen Schnack, you have some comments and questions with some interactions. Maybe you can go ahead and ask your question, please.
Yeah, Stefan, nice to hear you again, and a very nice talk. My question concerns that as far as I understand, your calculations are done classically. So the question is, are these terms relevant if we would do it quantum mechanically? Yeah, or how do we know that they are relevant? So my idea would be, is there, for instance, a 3-spin magnetic molecule where we would see the chiral interaction with the spins? What do you think?
I think this question is very relevant. So basically, you know, if you have very sharply noticed, I talk about a Hubbard model, then I project it into a spin model, but I did not tell you that this spin model is actually a quantum spin model. Whereas my ab initio calculation are classical magnetic moments, classical spins. So there is an additional approximation, which I'm replacing the quantum spins by classical spins. So therefore, I think that the derivation, which I showed you with this JAIJ on this lengthy equation, is absolutely valid, also in the language of quantum spin systems. So what we actually should do is really go follow the path of calculating a one-yearized Hamiltonian, do the downfolding, and then you really get your JIJs for a quantum spin model. Now coming back to the molecules. So if you think about solids, of course you have quantum fluctuations, but in general, you have such a large heat bath and electron bath that in a solid you have difficulty to see the quantum fluctuation. What I say is not fully true, because we have, of course, longitudinal fluctuations, which I did not include. But if you have a molecule now on the surface, for example, on an insulator, where you have only very few electrons scattering into the molecule and scattering off, then I think you can see this quantum nature, which I discussed also in the molecules.
Is there, say, a particular element or ion where the effect is stronger than somewhere else? I mean, would be manganese better than copper also, or doesn't that depend on that?
No, I think large magnetic moments are very favorable.
Okay.
So that means if you have, for example, a system where you have Hund's rule and large magnetic moments, the effect is strong.
Something like iron 3 spin 5/2 or something like that.
Yeah. Oh, that's fantastic. 5/2. Yeah.
Mm-hmm. You make him very excited. If you say 7/2, he goes ecstatic.
Thank you very much.
Okay. Igor, go ahead and ask a question and comments, maybe.
Okay. So I have a few. Actually, I have many, but I don't ask all of them.
A few.
This was very exciting talk, and you know this inspires many thoughts. But there's one technical, one conceptual question. That's all I'm going to ask. Let me start with the conceptual question. So I personally know, as I mentioned, a number of cases where biquadratic coupling is absolutely humongous, very, very large. And all these cases are good metals. One case is very well known as metal-based parent compounds of metal-based superconductors. And there are some other where biquadratic coupling even exceeds the nearest neighbor, Heisenberg. And in all those cases, it can be traced down to the fact that in metals, and the DFT is well reproducing that, the actual amplitude of the magnetic moment is not fixed. You cannot speak about spin 2 half or spin 1 half or spin 3 half or spin 2 in a good metal. It's always a non-integer moment. And some years ago, Ginyat Khaliulin pointed out that if you actually want to translate it into Hubbard-like models, you have to assume that you have at least 2 different spin states with a possibility of excitation between them. So it looks like obviously your calculations include all of that, but I don't see how that is reflected in these Hamiltonians you are mapping. No, and it's included in the Hamiltonian itself, but the microscopic model, I try to force it down onto Hubbard model, that seems to me that this important term would be lost. So this is one question. And the second question is very technical. How do you calculate spin spirals for incommensurate Q in DFT with spin-orbit coupling? Because the standard Sandratsky mapping only works without spin-orbit coupling.
Coming first back to the last question. So basically what we do is we do first a calculation without spin-orbit interaction, calculating incommensurate spin spirals. Then we basically store the wave functions of all these incommensurate spin spirals, and then do spin-orbit interaction in first-order perturbation. Okay, got it. Which is sufficient for Jaltinsky-Moria. Coming back to these spin fluctuations, which you mentioned. You know, honestly speaking, I have chosen the Hubbard model as a starting point, but I'm actually not convinced necessarily that the Hubbard model is the best model for metals. It is more maybe a model for oxides. So that's maybe, exactly right. Maybe a lattice condor model might be a better starting point. So I'm thinking of using a lattice condor model to derive effective Hamiltonians, but I'm afraid I will at the end not get different functional forms. So I have now, so to say, 2 spin 2 sides is Heisenberg. I have 4 spin 2 sides by quadratic. So maybe at the end of the day, I will have the same functional forms. So comparing these functional forms to density functional theory will not give me anything new. But what is new would be if I take the prefactor seriously and saying I derive my prefactor from the lattice condor model or the Hubbard model, the prefactors might be different. But if I have now a one-year-ized Hamiltonian, then maybe I can evaluate these prefactors and I might get different results.
Well, there's additional problems in metals. You have terms, energy terms, which actually depend on the amplitude of the moment. And the amplitude changes as you change your magnetic pattern and rotate your magnetic structure. And that's a huge problem. Because
this is true. This is true. I did mention this on purpose. I have chosen systems where this amplitude change is very small. I didn't mention chromium. For example, if you mention chromium, you know, you change your rotate your magnetic moment by 3 degrees, and the antiferromagnetism is gone. So basically, also for example, for many systems of iron, where the magnetic moment changes very much. But in low-dimensional systems, at surfaces and interfaces, the change of the magnetic moment is larger, and at the same time, the rotation angle, the magnetic moment changes less with the rotation of the magnetic moment. But this might be not true for iron germanium. For iron germanium, the magnetic moment maybe changes more so maybe one has to include this for iron germanium.
Thank you.
So let's move on to Hongbin Zhang. Please go ahead and ask your question.
Yes, thanks, Stefan, for this very nice talk. So I have 2 questions. The first one is, Stefan, could you please tell us how it is justified that we can neglect this 2-side anisotropy term, which is of second-order nature, but then, you know, usually people just neglect this one?
Yes, this is a really valid question. So, you know, I tell you the truth, what I think. We leave it out as long the experimentalists don't tell us it is necessary. But it is there. And we have also investigated the impact of the magnetic order due to this effect. And of course, it is a second order term. And it is in many cases smaller than the magnetic anisotropy, the single side magnetic anisotropy. But the nature is slightly different. And I would say not necessarily it can be neglected. Maybe it can be neglected for the systems we have studied.
Okay, good, thanks. So another brief question is about the chiral orbital moment. So do you see any connection or difference between the chiral orbital moments and also the conventional one?
Yeah, the conventional orbital moment, I would say, is an orbital moment in the sphere. This is, of course, not fully true what I'm saying, you know that. But basically, it is, so to say, an orbital moment in the sphere, where here you have, so to say, the orbital moment produced by a wave packet. So in some sense, the orbital moment you have normally is, so the rotation of a Wanyi orbital. Whereas here, the Wanyi center rotates from side to side. And that makes a difference. And if you have done basically a non-coplanar magnetic structure, then rotating left on rotating right, that makes a difference in the energy.
Thanks.
Okay. Daniel, go ahead and ask your
question. Hey, nice talk. But Stefan, I have a question about your derivation of the generalized model, including higher order spin interaction, proceeding from multi-orbital Hubbard model, the first part of your talk. What I don't understand, I didn't understand really what particular situation do you consider. For example, always maximum spin according to Hund's rule or not?
Yeah.
Or in particular, how many orbitals depending on the number of electrons. For example, if you have 2 electrons and 2 orbitals, that's fine, spin 1. Or 3 electrons, 3 orbitals, spin 3/2, also fine.
Yeah.
But if you have 2 electrons and 3 orbitals, then you cannot describe everything only in terms of spin, even if spin is maximum 1, spin 1, 2 orbital, 2 electrons, but 3 orbitals. You cannot describe everything only in terms of spin interaction because there will be also orbital degree of freedom left. And that's actually what we considered very long ago with Kugel.
Yes.
And you cannot really map everything to pure spin Hamiltonian. So which particular situation do you consider? Always number of electrons equal to number of orbitals?
Yes. Yes.
Only this situation.
Yeah.
Okay, so you don't have any orbital freedom left?
No.
Okay, I see. Good.
Yeah.
Thanks.
But, honestly speaking, if you would like to extend it, I would be very happy.
Oh, well, we did it long ago for simpler case when we have, say, doublet generate orbitals and one spin 1/2, one electron.
But,
doublet. But it can be generalized in principle for larger ones, but it would look rather cumbersome and rather complicated because it would contain all the terms you have with higher order spins, but also extra terms described with this orbital occupation, orbital ordering, and cross terms. So it would be very cumbersome. But in principle, actually, it might be possible to do. Why not? If it's worthwhile, because you consider metals, and of course, in metals, all these things are not directly applicable. That I agree with you.
So Daniel, you have something to do.
Okay, well.
The SPICE workshops, they usually trigger something. Some work. I'm glad to hear that. Marcus, go ahead and ask your question, please.
Yes, Marcus Gas from Karlsruhe. Stefan, I have a question concerning the properties of manganese germanium. So the question is whether nesting plays any role in for the Fermi surface of manganese germanium. So the question is whether this incommensurate wave factor, which is experimentally observed, is related to some nesting properties of the Fermi surface. So do you have any information about this?
No, I have no good information about this. I think, as first of all, you know, the wave vector is temperature dependent. It's for a long time, it stays at 3 nanometers and then it becomes 6 nanometer. So there is some Fermi surface dependence on the temperature, or maybe some dependence on the magnetic structure or temperature or something like this. So I have not looked at this, but it's a good question. Maybe one should look at it.
Jacob, you can unmute yourself now and ask a question.
Hey, Stefan, it's Jacob from Florida. I also have a question regarding the manganese germanium. Have you guys done any strain tests to see, or in terms of isotropic compression or anisotropic?
Yeah.
Strain? So how would this spin-chiral interaction depend on the distance of atoms in the strain?
So we have done the calculation for different lattice constants, and the physics does not change much. Of course, if you have a strong compression, then things are changing. But basically, the things are robust with respect to strain.
So the size does not change much, or it's changing sign or sign?
I have not published that, but I can give you the data. I will look at it.
Okay.
Okay, very good. So I believe those were all the questions and comments from people. I want to thank once again the 200 and plus people that showed up to the talk, but most of all to Stefan, to the wonderful, very clear, very, very interesting talk with a lot of details that I was curious about. With a short notice that he was given by Euro Microsoft, who is also to blame for this, and also for the plugin on the SPICE workshops. That I will send you another bottle of wine and after that. So with that, I wish you guys all a very good rest of the day, or rest of the evening, or wherever you are in the world. And we hope to see you next week here, where Hideo Ono is going to give the next talk in the series. So thank you all, and I hope you enjoyed it.
Bye-bye.
Thanks, Stefan. That was great.
Yeah, it was fun.
So we had about 200 people. Typically, there's about 30 countries or so. If you're curious to see how many countries you matched, I can try to send it to you. Okay. It's quite international, the whole audience. It's nice to actually see all the friends and names that you know, they don't see the names themselves, but I see who is on, at least in the Zoom side, and they generated lots of questions, you know. So this is actually really, really, really good. And there's Matthias with his.
I have some more questions, but I'll ask them on Friday.
Yeah,
okay.
You guys will see each other. You guys are in the synergy project together. Finding those hop wheels somewhere in there, you know, you're on these suckers, yeah.
Well, I have no doubt that Stefan will find hop wheels. I have more doubt that I will find hop wheels.
It's an advantage of having, you know, this is the thing I never understand, you know. We theorists have it a lot easier than you expect.
Yeah, I can tell you, you're more flexible when it comes to
we go grayer much sooner, yeah. So I never figured that one out, you know. If you see the theories, it tend to be grayer. But we definitely don't have a stressful life, yeah, compared to you guys.
Well, we're stressing about different things. Our problems are very banal, like the turbo pump is broken.
Ours are also, you know, it's like, can you do this? Like, oh yeah, I can do it. Here's the term. It's like, that's having to do with reality. I don't know. It's Trump. Trump will believe it.
Trump will retweet it.
Trump retweets it. That would be good, yeah. I will definitely put advertisement. Maybe not the type of advertisement one would wish, yeah. No, but I saw that there was quite well attended today. About I think all to 200, 250 people showed up in between both the SPICE and here Zoom together. And then I will post immediately now the talk. I will stop actually. Talk about that.
Right, I'll see you. I'll need to sign off. Thanks, Stefan. Thanks, Jairo, as usual.
Yeah, recording.